Hello, we are RISD Design AR, and we also have Case Western with us. And next slide. Next slide. Oh, there it is. Okay, interesting. Oh, well, my name is Selena, and my co-lead Bowen and I are the lead of design. And
hi, I'm Keenan. I'm from Case Western on the team, and I am one of our software co-leads.
I'm the other software co-lead. I'm Viola.
So the goals of our interface design was to reduce cognitive load, reduce the amount of mental steps to interact with the device, and then also be as intuitive and easy as possible so that even novice users could learn it. The way our interface works is that we have this small navigation bar on the left that floats, and when you select it, there's vitals, navigation, geonotes, and messages. And when you select it, it opens up a page to its left. And for example, if you select one, it opens the other. And there are two interaction modes. There's a button mounted to the chest where you can use tab traversal to navigate the design, and then you can also use your hands to tap through the interface on the actual HoloLens.
With the chest-mounted buttons, the goal with the buttons, of course, is to make sure that there's a few different ways that the astronaut can interact. So they can use, if their hands are free, they can use the holographic buttons. And if they're using one hand or if they don't want to reach up, they can use the chest-mounted buttons. We simplified everything down to 3 buttons so they can interact with the entire UI with just 3 buttons, up, down to navigate through things, and select to activate things. Next. We did a lot of testing and iterations on the site here. One of the things we quickly realized is that we really needed to reduce the number of hand gestures and triggers required in each flow. The astronaut really needs to focus on the task at hand, and they don't need to be interacting with the UI. So we slimmed everything down, simplified everything to the minimum possible number of interactions for every single feature we had. We also, in the same vein, reduced the number of functions. So you can see on the left, we have our original design for navigation, and then on the right, we have what we ended up with. We also tried to keep things intuitive, so we have this 3D line on the ground that the astronaut can follow to navigate. It fades from red to blue. That way, the astronaut gets a very quick visual indication of how close they are without having to kind of read a map or read a time or try and use numbers or anything like that. Same thing with all of the interaction gestures, right? All of our vitals, we condensed it down onto one page as much as possible. That way, the astronaut can quickly, at a glance, see everything without having to tap through or interact with anything. And all of this is part of the bigger goal of reducing cognitive load on the astronaut for using the user interface, right? So the user interface should be there to do its purpose and out of the way when they're doing astronaut tasks. In the same vein, we unified a lot of things together, right? So everything is in one entire pane floating in front of the user. There's not multiple different things popping up. This one pane means that they only have one thing to keep track of. Now, for hardware, we had 2 external pieces of hardware connected to the device. One was a GPS sensor. In order for us to make the kind of line on the ground work really well and kind of register to the ground very well, we need pretty precise upfinding. And so we use a high-quality GPS module with fast updates. We also use that to get that hardware to get the physical buttons to control the user interface as well. And all of this is connected over Bluetooth to the head-mounted display in order, well, basically so that we can package it as easily as possible. The other thing we noticed during our testing was that we needed to the HoloLens needs a lot of light to track stuff around it. So we used a set of work lights mounted onto their vest to do that. Each of them was 500 lumens, and we found that pretty much solved our tracking problems. We also did a lot of testing and iteration at JSC. So when we were here, we were prototyping different places and locations for the buttons. We found on the chest where the DCU is a good area. Certainly that's why the DCU is there. This is another kind of screen that we slimmed down a lot. We originally placed all the geological sampling notes that had been done onto the map, and then we decided to slim all of that down so that the astronaut could focus on their sampling task.
And then for the fun, when we tested it yesterday, feedback that we had were that the interface was really good with the spacesuit, especially with the additions of the manual buttons, and that the colors were really good indicators.
So what we learned from the mostly our previous user test and the first test day is that we need to implement early and fast. So this from our the UI user testing that we've been doing throughout the process. That due to remote work, resource limitation, and distance between our members, so we were spread out throughout 3 universities in the U.S., and I was in Rome, Italy for the last semester. And we were not able to implement our design into the HoloLens until very late in the process. And then when we finally did implement, we found out that what works on Figma is very different from what works in Unity, and what works in Unity is very different from what works on the HoloLens. Next. So yeah, we learned that we need to implement into the HoloLens during the first stages, even if like it's not like a final product. And then we learned to reduce, merge, and narrow down. So throughout the design process, our product got fewer and fewer frames, less and less functions, and that's when we know it's getting better. And then we constantly learn from the testing experiences that UI needs to give feedback to the user's actions. For example, red dots indicates recording, so that when you hit the video button, it gives you like some feedback. And then highlighting that indicates selection of the destination button, because there's like it's also because previously there was something wrong with the colliders, so the buttons wasn't like working super well, but it was like a cluster of like 10 destination buttons all in one place for the user to select destination. So that's when we learned that we need to give feedback once the destination is selected, so that you know selected the right destination, that you can begin navigation. And then moving forward, we're gonna iterate based on the feedback, the precious feedback that we got from the 2 test days, and then we're gonna implement voice triggers and eye tracking, and we're gonna come back next year. Does anyone have any questions? Okay.
Distance markers, because the geologist might like that too. If you say, hey, I'm observing a rock face, it's about 30 meters from here. They like those kinds of numbers. And it also may help the astronaut get this sense of like how far they've traveled. So distance indicators along the path, and then maybe some summary in a stats box somewhere of like, oh, you've gone 2.3 kilometers. So then if your buddy keels over, you know how long you have to get him back to the rover.
Yeah, thank you for the feedback, and we like that idea, and we'd hope to add it in future, yeah.
Actually, my question was somewhat tied to that. As you pared down what you were capturing as far as your notes, is there anything you thought to add? I agree. I think distances is important to know. I think also if you have, I noticed when you said it was better to be able to make an indicator that you had done something successfully. That's important to note. Is there also something that you could have off to the side with your tasks at hand? So that way you could, even if it goes off at the end, if you know you have to complete 4 tasks, knowing that, yes, you hit the record button and it captured is important. So you're not falling back later and wondering why it didn't capture.
Yeah, so we breezed through a couple of our features there, but it does show you a list of photos and videos that you've captured. So you do get feedback there, and certainly I think one of the things that we've taken away is that a lot of the very small details for feedback are extremely important. So having more feedback on some of our interactions is definitely an important thing to add.
Hey, Rizdi, great job. I think one of the things I was most excited about for your team is that you're purely a design school, and of course you have quite a few other people on the team, but my question for you is, how did you merge some of your design concepts from a design school and then merge them with also some of the hard engineering requirements? And was there any difficulty, challenges you faced there? Are there elements that we could start incorporating from a design aspect for next year's challenges? Yeah.
Something that we did was we actually took 2 years. We missed the deadline for the first year, and then we spent that year doing research, which gave us a lot of extra time to understand the problem space. And then we also, when we recruited the engineers, we also had them start designing a little bit with us after we have some research, just so they have like a little bit of a picture. And I think that probably helped a lot because they felt more attached to the design. Yeah.
Thank you.
I have a question about the cognitive load aspect of your design. So in the future, how do you anticipate handling more voluminous loads of information, right? And so astronauts have to process a lot while they're doing an EVA or just in general. How might your design accompany that or account for that in the future?
One thing is that we just didn't want it to interfere with whatever task they're doing. So like the buttons on the chest can turn off all the interfaces if it interferes. Yeah.
Thank you.
No, I was just saying thanks. Sure. Quick question, and actually this is maybe a little bit more for Kate, but it's based on a lot of the teams that I've seen. The biometric data that you guys put up there, I think a lot of the teams I've seen are trying to figure out what to show, where to show. How much do you care as an astronaut about that, and how would you like to see it if you would at all?
Yeah, that's a great question about the biometric data. So just, right now we have our DCM display, and so we can toggle through things like, oxygen left. We can't really get any information about our own heart rate. The surgeon monitors that. I was thinking about when you were showing that the biometrics displays, I was trying to think about which of those circles maybe would I want in like the lower left corner unobtrusive. So I think you could do one of two things. You could pick like a few key parameters. So things like, oxygen and then like a green dot to indicate the health and status of your system that like turns yellow or red if you've got a caution warning. I don't really care if my heart rate's like 72 or 83, but I want to know if it starts going above 150. So something that's hidden until it hits a certain limit threshold and then pops up maybe with a color to alert you, like yellow, oh, you're working a little too hard. I do think some key things about your consumables is something that we always have on the DCM. So I think one of the questions is do you want another place to see that in a little more heads-up manner? How many of those do you want to display, and how many do you want to make hidden until they cross a threshold value? But I think thinking about all of that in the design space would be pretty cool.
Yeah, we kind of appreciate the feedback and went back and forth a lot on our team about that. We actually do show one piece of information on the heads-up display. We show the minimum remaining time, so the next time that you're going to run out of oxygen or battery or something similar, right? the problem we have from some perspective is with an AR head-mounted display, you have a very small field of view, and anything you put in that heads-up area, it takes up quite a bit of it, right? So we really pared it down to the minimum for heads-up type content.
That could maybe be if you do voice activation, not have it display, but then if I just say time left, it pops up for a few seconds.
I just have a comment. I found it fascinating that you all did this remotely with one team member internationally, right? And you worked over for a 2-year period. So we're looking forward to seeing you back next year.
All right, and our next team up is Wichita State. Team Harvey.
Hello, my name is Bill. I'm here today with Philip, Vadif, Ramil, Abby, Valerie, and Shayo. We're Team Harvesters from Wichita State University. Our user interface is called Holographic Augmented Reality Visualization for Exploration, otherwise known as HOIVI. We're a multidisciplinary team consisting of aerospace engineering students, computer science students, human factor psychology students, and innovation design students. So just a brief little summary of our design. Hey HOIVI, play video.
We decided to implement the user interface on the top of the peripheral vision to minimize distractions. The display shows all of the features such as status or chat. The heads-up display follows the user's gaze. The mission log displays tasks and automatically crosses the tasks when they are complete. Status and vitals are color-coded. Green indicates normal, orange indicates warnings, and red indicates danger. The camera function enables the user to capture images which can be revealed right after for verification. We have preset sample features such as shape, color, and texture, but there is a keyboard option and microphone option in case they want to input more detailed information. Our tour information list provides the correct tour for the specific geology environment. For example, use tongs for rocks, or use rake for gravel. The chat feature automatically appears when there is an emergency sent by another member. The user can use preset messages or an integrated keyboard or voice recording. A map indicates where the emergency is signaled.
Open voice command list. Oh, sample collected.
Our voice commands are organized in a list and easily accessible.
So some of the major UI user interface problems and fixes that we had were, one was clickable buttons. For clickable buttons, we added in borders to indicate clickability. For example, chat has a border, while on top, oxygen does not have a border. Another problem was for sample recording. At first, we just had a camera, and then we decided to add in different preset design features, such as size, shape, and color, and also keyboard for more detailed information. One of our major problems that we had was for navigation. So at first, we had a blue navigation line. We had the blue navigation line that navigates the user to a select waypoint. So the user can place down different waypoints. And there's also terrain sensing to categorize different hazardous objects. But due to some problems, due to some bugs, we had to include an aerial map instead.
So upon some reflection, we came up with some positives and negatives. So one of the positives we used was or that we mentioned was that we use Adobe XD, which is a 2D software designed to kind of go through those quick and dirty usability problems and efficiently pick those up early on. And we also had a huge focus on all parts of the design, so not just programming, but also design and research. Click. Yep. One more click. Thank you. So one thing to note is that we had 9 successful outreach events. So one to note on that bottom left picture is that we placed 3rd place at the GRASP conference at Wichita State University. But then going over some of the negatives that we found is that we had one programmer. So, but we did produce a good design after that, but we really relied on him. But it worked out in our favor. And then another thing in the bottom right is we did a retrospective, and we found that we could improve in some areas in our design and our team. So we decided to set more detailed goals and deadlines, just to keep us moving along to the objectives. And then it also, just providing consistent updates for the team. Maybe some of the design team knew something that the programming team didn't, so we made sure that every Thursday we were updating the team in our weekly briefing. Click. Perfect. So several takeaways that we came up with. The most important things is that, one, this was a really unique opportunity for us, especially Radif, our freshman, who actually mentioned the other day in a lunch that this was my favorite part of my freshman year, which I thought was amazing. And secondly, this was just an opportunity where we can learn how to communicate with multidisciplinary people among our team and use that for future projects or careers down the line. Next. Next. Is it going? There it goes. Okay, so 2 rules that we came up with after this whole experience. So one, never forget your photo ID when you go to the airport. I'll just say that, Radif. Secondly, don't take your programmer to the ocean without a backup pair of glasses. He did lose his glasses. So we had this, that was the other day, Sunday. But lastly, we appreciate this opportunity to bring together different people with different backgrounds with one common goal in mind. But we also want to acknowledge some of our mentors, Amanda Smith and Ryan Amick, and our WSU advisors, Kristen Smith and Maggie Schoonover, and then also the NASA Suits team for supporting us throughout this process. Thank you.
I have a question. Thank you for your presentation. You were very intentional about having a large interdisciplinary team. What challenges did that bring to the table for you?
Answer that?
Can you repeat that one more time? Sorry. Can you repeat that one more time? Sorry.
What challenges came up for you because you had an interdisciplinary team? What challenges did you face because of that?
I think one of the biggest ones were communication. So letting the other team know what the other team was working on. We actually split into 3 different teams. One was a design team, programming team, and research team. So the research team first the research team would do some research on the design. Then the design team would develop that design, and then they would implement that into the programming side, and then we would do more research on the programming side. So it was a kind of a cycle, but I think one major thing was communication between different groups, and we actually found that through the retrospective that we conducted, that we needed more communication, letting the other team members know what we were working on and what was going on in the other teams.
Thank you. By the way, that never happens at NASA.
Or Microsoft, ever. Actually, even to go along with the last presentation, I think adding scales to the camera functions, and also to where you're walking to when you're collecting samples, being able to tell, you might designate it as small, but being able to kind of get a size scenario for it might be helpful. I think also, and this probably could go to a lot of other groups, I would imagine all, being able to adjust for different types of lighting. I know you guys have all focused on that. I think moving forward, there's going to be a lot of test cases with infrared and ultraviolet, just so we can help kind of determine what kind of composition there is in the rocks and what not have you. So that's something to think about also for further.
Quick question this is kind of for all the teams, but I'm going to start with you guys since you asked it. Looked like a lot of you guys have different ways to interact with your system, voice commands versus manual, either hand gestures or buttons. As you guys played with your system, what did you find you preferred
as you interacted with it?
So definitely in a dark setting, we definitely preferred the voice commands because it was dark and the user couldn't really click. We did want to implement eye tracking as well, but we didn't get to that point yet. It was in our proposal, but voice commands definitely helped a lot.
One comment and one question. So the question is, I was wondering when you said where you decided to put the display, it was kind of towards the top, but I noticed in the video it was a little bit in the sweet spot of your point of view. Have you done, A/B testing or some kind of testing where you look at the same user in a few different, like on the side or on the bottom places for the display?
If I'm answering your question correctly, so the video is a little off. So when we record the HoloLens, it somehow puts it a little lower, but it is at the top of their field of view. But we also incorporated a button where they can manually move that up and down and also freeze it where it is. But it's always following you at that top where you set it. But we incorporated that up and down. I think, I guess we might want to do some more testing, even maybe with depth as well. But yeah.
That's nice to have the adjustability. And my comment was I really liked the part of your process where you had the Post-it notes and you looked at what was going well, what wasn't going well, things that you wanted to keep. I just really encourage that. I think that's a great way to do some, midway through your project or at certain milestones kind of evaluate. It helps particularly a big team like this get on the same page, and sometimes you can get really creative ideas coming out of that. So great job in your project management with incorporating that.
Thank you.
Hey guys, awesome job. I'm so kind of excited and proud for you last night when Nick told me that you sent over a Lunar Star message. Can you talk through a little bit of your challenges on the Lunar Star messaging and the telemetry stream, and if you experienced any, and then how you kind of overcame those?
Do you want to answer that?
So originally, when we did the lunar search thing, we didn't use the right API for it. So when we came here testing, I believe on Friday, we were talking with the person who runs the server, and I was asking, like, how do we do the lunar search thing? And it's like, oh, it's on this URL right here. This is how you receive it, and this is how you send it. So it's just another, sleepless night for a programmer to just implement that right away. So it wasn't too hard because we had a system in place already. It's just we didn't know where to fetch it, and then we had that chat since the first 2 months of this semester. So everything went smoothly in that direction. It was just we just need to get that information and then use it in some way.
Thank you. That's exactly what I was looking for.
Mm-hmm. Thank you.
All right, thank you very much. Great job. Great job. Our next team is University of Southern California. And we have two, right? So here's our first USC team.
Come on up. Come on. We got a few of us, so we'll have to make some room. Come on. Come on. Don't be shy. It's our moment in the sun now. As you can see, we brought a bit of a contingent here with us at the JSC, and we're so happy to be here. Ladies and gentlemen, my name is Evan Cooper. I'm the program lead of Team Aegis, and on behalf of our advisors, Professor David Barnhart and Dr. Garrett Reisman, as well as Dr. Jessica Barnes, I present to you Senva. If you'll roll to the next slide and play the clip. Oh, I do. I do, but it should be a YouTube video. All right. While we're getting this set up, so I'll talk a little bit about our team. So we are, as I see a lot of us are here. We are a cross-disciplinary, very large team with about 60 members overall, and this is our first year in the NASA Suits Challenge. So I was going to talk about this a bit later, but that provides a whole host of its own difficulties trying to spin up essentially a small or medium-sized startup. And one of the things that I learned immediately as soon as I took over the role of this team is I needed to find a strong leadership team to help support me and to help take care of all the things that I could not do myself. So all of the folks that you see behind me are the ones who took care of basically all the real work. I just helped with whatever, getting coffee, doing fundraising, things like that. So it's all these folks behind me that really made Stanford as good as it is today. And how's our video coming back there? Huh? There we go. Enjoy. And thanks very much for staying in for cutting that together. All right, so who we are. So as I said, my name's Evan, and then we also have behind me on the stage, we have Darlene, Spencer, Akshita, Andy, Bass, Jennifer, Isaac, Patrick, Rohan, Sophia, Stanley, as I said. Will is not with us. He went back to New York, actually, and then we have Zoe as well from University of Arizona. As I said, our technical advisors, Professor David Barnhart, Dr. Garrett Reisman, and Dr. Jessica Barnes. We'd also like to give a special shout out to Dr. Culbertson and Dr. Olson for all their assistance on this project. So to highlight some of our design philosophy behind this project, we have a systems engineering based approach where you can see all of the different inputs and outputs that we were expecting from each of the systems, and we wanted to make sure that all of those linked together so that all the data got to where it needed to go, when it needed to get there. Along with that, we have a human-in-the-loop informed approach where we had Darlene execute sub-studies on retired astronauts, figuring out when they have an AR panel in front of them, what do they actually want to see and when do they need to see it. And as I said, we are a cross-disciplinary driven group. So I'll go into a bit of detail on some of the key features of our product. We have our A-star pathfinding algorithm on our digital terrain mesh. And you can see that we've got the little houses there that represent the stations that we would see in the rock yard. We use an A-star pathfinding algorithm to route astronauts and whoever else is using this program around hazardous obstacles, maybe a little bit of uneven terrain. And that allows you to get from point A to point I or anywhere in between. Just by using our point-and-click menu that you saw in the video. Along with that, once you have chosen your destination, then we have our yellow brick road, which is more of a blue blob road, but don't say that, that allows you to see your path right up in the air so that you can follow it without having to, continue to look at the map like we're, old school, bringing out the road map from 20 years ago or so. For our short-range navigation, this is one of our most like awesome features, and I get so jazzed talking about it. So this is our terrain markers that are inspired by Hideo Kojima's Death Stranding. Excellent game. But you can see up there we have our red and blue markers. And so what happens is we have the sensors on the HoloLens actually taking in the terrain, creating the mesh, and then using ray casts to measure the normal in between the points. If that normal is out of bounds, then it turns to a red that shows, oh, this is not a safe area to step, such as right here. Or if it's blue, then as they're walking around, they can say, oh, okay, that's probably pretty good to step at. So with that, we had originally 100 markers and some opaque shapes. We switched over to our new system, which has 625 markers, and moved to green circles and red X's to tell you where you can go and where you shouldn't go. Our Lunar Star, this is our Lunar Star panel. We have our navigation that allows you to navigate to the distressed astronaut, as well as the pre-canned responses, en route, roger, and standby in order to update your distressed companion as to your status. We also have our virtual assistant, which is one of our key features. So this allows you to say, hello, Eva, and allows you to access your vitals panel as well as using speech-to-text and text-to-speech with dialogue management. So you don't have to say the exact words of what you're trying to get to. It actually interprets your meaning. And this is all done offline. It's not using an internet connection or anything like that. Instead, it's all trained so that it can be on your person so that as you're exploring the moon or wherever else, you don't need an internet connection the entire time. Some of our future work is we're looking for dynamic modification of our digital terrain model so that as the astronaut is moving across the surface, if we have some LOLA data or anything else like that, now we can get the actual person on the ground modifying that terrain so we can get real up-to-date readings. Also looking at using eye tracking for both input and to monitor the alertness levels of the astronaut so that if they're kind of like getting a little woozy or things like that, we can use the eye tracking to really track that data. Along with that, using machine learning for computer vision for geological sampling, adding in some extra peripherals such as a haptic alert system as well as alternate input systems to get away from the gesture-based control, which may not be viable using a pressure suit such as the XEMU or any new suits coming along the pike, as well as using the LSAR to figure out the ETA to the nearest pressurized volume, both if you are walking at a normal speed of 2.2 meters per second, for the Apollo walking speed, or if you need to actually take an incapacitated crew member. Cutting that down so you can see exactly how much time you have to get your companion to a safe environment. Alongside that, a dynamic warning of the walkback limitations for some of the missions that are a bit more out there away from the home base. And this is the full list of our team members as well as some of our gracious sponsors. Thank you so much to everybody who helped get us out here. It was definitely not an easy thing, but we have appreciated every single opportunity that we've had today. And this has been an absolutely amazing trip. So thank you all so much for allowing us to come out here and to present to you our product over about 9 months of work. Thanks very much. Any questions?
Hey guys, yes, you are absolutely a startup. So with 60 people on your team, you mentioned that it was a difficult integration problem, but how did you, I saw that you had a systems diagram. Did that help you as a communication tool? Were there other ways that you gapped that communication between 60 members in various teams?
Yeah, so I'll let Spencer answer that partially, but I will first off say I have enough meetings in my day job, and I didn't want to add more and more meetings for everybody. So immediately we said, okay, we'll have some very basic general all-hands meetings, but from there we immediately split into focused teams that have different capabilities and different responsibilities, so that those small teams could meet on a more regular cadence, such as every week, whereas the larger meetings maybe once a quarter or so. I think we had overall 4, so that we could cut down on the amount of time that was just kind of me talking to everybody on a Zoom call or things like that. I believe the systems engineer, Andy Artsy, who helped create that diagram, that was super helpful for me in particular to understand, as I'm an astronautical engineer, all the different systems that needed to work together and what resources needed to go into that.
Yeah, so adding on to that, So I would say we had two major features as to how we organize. First being we adopted the agile development cycle. So for those unfamiliar with that, essentially every meeting is weekly. So it's a weekly sprint, and the meetings consist of three things. So first of all, updates. What have you done this week? Second of all, bug squashing, because, well, 5 minds is always going to be better than 1. And finally, what are you going to do this week? And this development cycle allows for a lot of flexibility with a college student team. And finally, I'd say that we organize our teams in a way where we prioritize a more combined arms approach rather than here's a team that does only artworks, and then we're going to have to pass it on to this team. Oh, this team says artwork's no good. Okay, we got to pass it back. So we wanted to make that as integrated as possible. Yeah, which is why in our UI team we had both programmers and designers.
I know we heard from some of the other teams that they realized they wanted to streamline once they started. What kind of changes did you make to simplify things? And moving forward, is there anything you plan on adding or maybe changing the way you did it?
Absolutely. So some optimizations that we have done, which allowed us to improve from 100 terrain markers to 625 terrain markers, for example, is decreasing the color depth of the HoloLens from 24-bit to 16-bit. We also started building in master mode, which is far, far superior to both release mode and debug mode. On top of that, some additional features that we've now found out that we can incorporate is we can actually increase the density of terrain markers even further, so keep pushing that limit. And on top of that, we've actually tweaked around with the spatial mesh that the HoloLens actually creates. So we're looking to actually improve our DTM updating feature. And on top of that, make our A-star a whole lot more, dynamic. And finally, I'd say another, like a stretch goal is possibly asking NASA to provide us a DTM with much, much higher fidelity of the Rockyard or whatever future test site that we have. Because, we just relied on consumer-grade Google Earth, high-altitude satellite photogrammetry. And that definitely doesn't pick up like boulders and tiny rocks which is why we got the terrain markers to help us out. So they work in tandem and works great, I think.
Yeah, and alongside that, I think setting a clear sight on the goals that we had for the project. This was our first year, so we kind of tried to do everything all at once. Setting a clear sight on what we actually want to accomplish is, I think, going to be, for next year, a much stronger product when we do that.
Can you expand just a little bit more on what you mean by making A-star pathfinding a little bit more dynamic? What elements would you add there?
Yeah, so the A-star Pathfinder that we have right now is currently working on a pre-generated DTM, which is the 3D map that you see right there. Yep. That's collected using Google Earth. However, you'll notice that there are holes in the mesh, and that's simply due to that's the nature of high-altitude photogrammetry. But if we had a solution, such as using terrestrial-based photogrammetry, or my favorite, drone-based photogrammetry. So you have this low-altitude drone that basically flies around, collects like maybe 200, 300 pictures, stitches it together into a 3D model. That allows us to map out the terrain with much, much higher fidelity. But of course, if we were to consider this in a real-life scenario, such as on the moon, if we go ahead of time, like maybe a couple months, get some LOLA, photogrammetry of the moon, things could possibly change. Like, I don't know, maybe, a new asteroid kind of creates a new crater, then our LOLA photogrammetry is no longer, the most up-to-date. So I think a reach goal that we want to do is update the DTM as the user walks around with a HoloLens, because a HoloLens has a fantastic albeit limited suite of sensors that can actually update 3D meshes as you scan the environment. So it'd be really nice to just literally update that map. And if you have like an entire team of astronauts, only one astronaut has to update it, and everyone else would get a map. Mm-hmm. Absolutely. Mm-hmm. Yeah.
Hey, I really like the feature recognition for your short-term navigation, have you looked at how that changes in different lighting conditions? You know, we've got really harsh shadows on the moon and maybe not a lot of light in South Pole.
I'm glad you asked. So, yes. So, I'll let my brother explain a little bit about how we tackled it. But so, short answer is we actually did go to like the worst, or Riley guided us to the worst spot with the harshest lighting, and it worked like a charm apparently. But Stanley can tell you how we fixed that.
Actually, it was Evan and I. The night before, so Saturday night, we actually went to Academy, which is like this outdoor supply shop, and we were trying to figure out how we can like secure camping lights to the astronaut or the user, and we ended up buying a fanny pack and literally strapping on 2 LEDs on like waist level, and we called it the Halo belt. So that's.
Yeah, for that, we determined that using the waist-mounted belts allowed you to illuminate your path as you're actually walking. Previously, we had only used 2 head-mounted lights to allow you to look at your hands, get light to where you're actually looking, but we still need that diffuse light so that the sensors can actually recognize the terrain. So a similar system for that, for these spacesuits, I think is going to be desirable, especially in those super harsh conditions that we saw out on the rock yard.
Yeah, and the other thing to think about too is the conditions can change fairly rapidly. It sort of depends on where you're going and where you are with the sun angle and everything, but certainly in a space station EVA, it goes from bright to dark, and you're like, I mean, it is just, wow, it's amazing how bright it is and then how dark it is. So being able to keep up with those real rapidly changing conditions, some kind of sensor on your light pack and adjusting might help your interface a little bit more. And then the other question I had was we're testing this in gravity and we kind of have to walk here. But if you see the Apollo astronauts, they're doing this kind of bunny hop, lunar shuffle. And so I'm wondering how this, is a projection of the terrain features far enough? How does your mesh network accommodate some vertical lift in each step because you're coming up and down versus going straight across?
Yeah, so the mesh system actually works on a pre-generated mesh. Well, I shouldn't say pre-generated. So it's a little bit of a mix between pre-generated and dynamic. So it saves the mesh wherever you have traveled, and it generates it if you have re-traveled to that spot. So theoretically, yes, we can actually have the astronaut hop, and then the mesh will just it's almost going to be like you're moving in a game world, and that's what the HoloLens thinks you're doing, and it sees that, oh, you've moved 6 meters in front, for example. Then it just loads the next portion, and you'll see the next portions of the markers. So what you're seeing here, the range of the markers is actually configurable. That is dependent on the how much of mesh you have actually generated at that moment in time. So we actually set the cutoff over there just to save on computational resources, because we were like, oh, well, average human probably doesn't need to see like 10 feet like beyond. But on the moon, we do understand that you're probably moving at a way faster rate because you're doing that bunny hop. So, we can move that render distance however we like. Mm-hmm.
Thank you all.
And next we have Team Arsis from Boise State University.
Good noise.
EVA missions are more than the research that's conducted, as they have and continue to inspire generations of innovators. As we compete in this challenge for the 5th year in a row, we've had not only the opportunity to develop XR lunar exploration tools for NASA, but we've also had the opportunity to conduct a lot of outreach and touch the youth and to help inspire them take paths beyond our surface. To introduce ourselves, we are Boise State, and we have created Arsis as our solution to the NASA Suits challenge. So we develop on a augmented reality framework called ARSYS. It stands for Augmented Reality Space Informatics System. So we developed this year by year to help fulfill the challenges given to us by NASA, as well as adding in a few other features that we find would be useful for EVA missions. Our biggest strength is the addition of virtual reality, which creates another dynamic tool for the mission control to use to help assist, navigate, and communicate with the astronaut. By using ARSYS's 4 core features, the HoloLens 2, the EVA rover we have, and an AR ground station and a VR ground station, the mission control or the user has the ability to communicate via telestration, input augmented display, and navigate. This button does not work very well. Okay, so you have to press this one.
All right, so we're going to get in a little bit more specifics of what actually makes, like what our specialties are, like the things that kind of set us apart a little bit. So she kind of touched on the ground station a little bit earlier. And so basically what that allows us to do is it gives us real-time mesh capture and reconstruction in a VR headset from the HoloLens. And so that's basically kind of like a catch-all fail-safe. If all of our other systems aren't working the way we expected them to, we can use this to at least know what's going on roughly in the environment, and then we can draw annotations and notes that pop up as holograms in the HoloLens. And so that's kind of like our catch-all system. You can kind of see a little GIF right there on the top left. And to explain that a little bit, you're seeing the point of view from within the HoloLens running our ARSYS system, and then in the top right corner of that is the meshes coming through to a VR headset remotely over the network, and then we can draw notes on it and go back and forth. The next big thing that we have is our Robotic Assistant, which is new as of this year, actually. And the big advantage of this is that we can do video feedback to both the ground station and the HoloLens from the rover. It can also be controlled from the HoloLens, and in the future we want to make it controlled from the ground station as well as kind of like a backup. And this basically just gives us like another set of kind of eyes out in the field, right? You know, if you see kind of like a dark crater or something, you're not sure how steep it is, you don't have good information, you can send this out ahead of you to kind of check the area and kind of investigate before you go in. There's some more things we want to do with this down the road, but as of right now, that's all it really does. In the future, we'd like to look at doing, like using the LiDAR to scan environments, maybe collect meshes from the rover as well, in the same way that we do with the HoloLens. Another feature we have is our arm retained menus. And so this is basically, these provide natural hand interactions and quick access to menus and information that are tethered to your hands and arms. So you can just pull it up and look real fast if you need it. If you need to tap something, you can tap it. All of it can be activated with voice commands. Everything's very redundant, so you have multiple interaction methods for everything. And then finally is our legacy code base, kind of a general term there. But essentially, because we've been a team for 5 years, we've had a lot of time to research and develop on a lot of systems. And so there's a lot of things we have kind of going in the background, and a lot of things that we can pull into our project if we want to. So for example, for this challenge, we had a lot of features that weren't really necessary, so we removed them. But if we needed them in the future, we could pull them back in very easily. So yeah, that's kind of our secret sauce here.
I'm just going to go over very quickly. All right, yeah, this is probably better. I'm just going to go over very quickly the 4 main components of our system, which Megan already touched on, which is the AR HMD, which everybody here is familiar with, the HoloLens 2 at this point, which has all the main features that we use for everything. The 2 ground stations, VR and desktop, which are ways for sort of mission control to view the environment of the person in the HMD, see it as a topological mesh, and annotate on it. Then finally, the rover. I'm not going to touch on this too much because we'll have more time for questions if we do it that way. But the rover is able to move around based off of commands given via an AR menu and send video feedback back through menu.
Hey guys, I'm Mark. I was given the privilege of I'm one of the main developers for ARSYS. I was given the privilege of helping Sky and our mentor Darren navigate through the rock yard on Friday and Monday. This year we met with an interesting challenge. This is the first time where we're testing outside and at night. Our team came up with a 3D printed solution for this issue. It mounts on top of the HoloLens and is a camera light with high FOV. Sky and Darren had no problem whatsoever navigating through this terrain and had minimal tracking issues. I'll also say, with the diffused lighting, it also helped with pictures and geology sampling, as it didn't drown out a lot of the refined features of the rock. And speaking of geology samples, our geology sampling tool, it worked pretty well. It was designed to give the astronaut as much options as possible in terms of how much detail they want to give. There's 3 forms of input, whether it's from our sample description, voice input, and there's, what is it? Oh yeah, it's all good. But yeah, basically you can have either, voice commands. Oh yeah, audio. Either way. Yeah.
All right.
But testing week went really well.
Wow. So we're a smaller team. We've got about 6 people here this year. So we try to focus on experimental stuff, and sometimes things don't work out. So we try to stay scrappy and stay innovative. So Mark went over all the stuff that went well in testing. We had a lot of other stuff that didn't go so well, as pretty much everyone here can probably relate. But in conclusion, as a group, our whole goal is to get new features that haven't really been tried before in this environment, either developed for the HoloLens or augmented reality in general, or VR, or even stuff from game development. Try them out, see if they work. Sometimes they do, sometimes they don't. So over the years, we've brought in a lot of new things that haven't been seen before in suits, from the VR telestration to mini maps to the rover this year and other features like that. But even more, we've had a lot of features that didn't work out and didn't make it all the way to suits or are still in development, like fixing drift via cloud anchors, or what are some of the other ones we're working on right now? I mean, the rover kind of fits in that category. It wasn't completely there at the time of testing. Oh, yeah.
Going over one of the team's options, basically 3D topology. We were thinking about, 3D scanning an area and using the terrain mapping data to use area targets to recognize where you're at within the area target. And that was definitely one of the ways we were thinking of aligning our targets without that telemetry.
So yeah, for sure, lots of research. And over the years, we try to bring in as much of the stuff that actually works into our project as we can. And that's the overview of what we do as a group.
Not really a question, just an interesting observation that to me tells me how good you guys are doing what you're doing. There's 2 things. We have a system that we've built to try to create a virtual environment for our ground team to follow the crew members when they're doing EVAs on orbit. So you guys have really clued into the benefit of that. Sort of you figured that out on your own. The second thing is it's interesting, our Canadian partners have proposed a rover very similar to what you guys have shown here. Be interesting to see what they think of and versus what you guys have come up with. But it just tells me that this process is really working for you guys, and that's to me one of the big benefits to us, to having you guys thinking this way. You guys have latched on to a lot of the same problems we're thinking about now today too, so it's really cool to see how you guys have done this, especially with a small team.
For sure, it's a lot of fun to think about these things and think about what solutions would work for them.
I appreciate the fact that you talk about you're an innovative group. Could you talk a little bit about how you transfer your knowledge from student to student? Because at some point you're going to graduate, right? And so how do you all keep the innovation going within your program and transfer that knowledge?
So the main answer to that is documentation, which there's been a push really over the last couple of years with this project to document everything on the project as these people are graduating that were part of this original team. We've got extensive video on most of the features that exist, written documentation. I've written a couple pages on just how to set up the project and build it for people who are very new to the project. That is one big, huge part of it. And the other big part is making sure that as new people come in, they're properly onboarded, given an opportunity to explore the whole project before they're really given responsibilities, and otherwise push people into a role where they feel like they can make small contributions instead of being intimidated by the size of the project, because it is a big project. It's almost, 8 gigs right now? Really big for a Unity project for a scenario like this.
advantages of that is that, okay, yeah. All right, so one of the advantages of doing that is that we try to make it so that when there's new people on the team, if there's something they want to do or some little low-hanging fruit they want to go for, we're like, yeah, go for it, do it, I'll help you do it, let's make this happen. Because oftentimes I found this myself, until you do something on the project and really push some code and it does something and it builds and you did it, you don't really feel like you're part of the team. You know what I mean? Until you do that, you're just kind of oh, I'm just here, I'm just in the meeting, I'm just learning. And so it's really important when someone joins the team to get them in and contributing as quickly as possible, because it makes them feel like they're part of the team. And then oftentimes they learn a lot more in that process. I mean, that's how I learned everything I know. So yeah.
Technology is hard sometimes. Great work. I really do like Chris said, I like that you came from it at a lot of different angles, and I like that a lot of it can be built upon. I think the rover would be also really great later on for collecting samples. I think that will be huge. I really like the topography, how you were doing the mapping there, because it changes so often and how it can be, piled on top of one another. I like the combination of all the different avenues. I'll be curious to see what you guys do in the future. Thanks.
Thank you.
Great job, guys. I commend you for being so courageous with very large features and being a small team. I think that is very brave of you, and that is exactly what you're giving us, the things that we want to see, and you really followed the mission description. In the future years, I think, and you probably learned this a little bit this year, but because you have such a smaller team and you have a lot of big features, I would find a point in your schedule where you come to a close on what those feature sets are going to be, and then bring them forward, because everything you chose to show is every single thing we wanted to see, and really curious to see any sort of first-person views of your telestration capabilities. So thank you for doing that, and I'm looking forward to see what you bring back next year.
Thank you.
Okay, and now we have Team Claus from the University of Michigan.
All right, hello everyone. My name is Hope. I'm a UX designer, and I'm here with my team Claus at the University of Michigan. We'll be presenting to you Hoshi. All right, so just a high-level overview. We mostly focused on navigational features, geological features, and we also worked on a voice assistant called Vega for user commands and inputs. We have our primary interactions are controlled by voice. We also have secondary interactions by physical touch, like fingers, hand raise, and we also make sure to give feedback through visual and audio cues as well. I'll just show you a nice cinematic we've made. One of our UX designers, Clement, worked on this, so pretty cool. Hey Vega, open menu. Let's take a look at my vitals. Looks like I'm good to go. MCC, Neil and I are looking good to head out to the geosampling sites, heading to Station Alpha now.
Roger. Your vitals all look positive. You're good to go.
Hey Vega, open map. Okay, let's get directions to Station Alpha. And we want to go to Charlie next. Let's get these directions. Okay, seems like I'll be using about 3% of my oxygen. It's going to take me around 7 minutes. Hey Vega, start navigation.
Hang on a second. I didn't see this on the map. Let me go check it out.
Gotcha. Just stay within the radius you're supposed to.
Don't worry, I will. Oh wow, this is interesting.
Hey Vega, show directional aids. All right, mission control, I've arrived at Station Alpha. I'm about to start sampling.
Roger. Everything looks good on our side. Proceed with your mission.
All right, I found an interesting sample here. Hey, Vega. Hide directional aids. Hey, Vega. Open notes. Alright, let's just open this one I've already created. Hey, Vega. Add a sample. Let's take a picture of this. Alright, looks like my pictures have saved. Hey Vega, start transcription. I've just arrived at landmark A about 4 minutes into my EVA. The sample I'm holding is about 2 inches by 2 inches by 1 inch in size. Its color is black-brown, texture a bit grainy, and it's pretty light in weight. I will end the sample here. Hey Neil, I'm done. Where are you? Let's head to the next stop. Neil, do you copy? Neil, do you copy? Mission Control, something's wrong with Neil's suit. I'm heading towards him ASAP.
Roger. Proceed with caution. We'll try to monitor him from our side.
Alright, that's the end of that video.
Sorry about that.
Alright, so trying to get a look at how the heck did we come up with our design, how do we get here. To first start off, we conducted a ton of research to try and understand, like, who are these astronauts, what are they doing, what are they having problems with, and after that research we kind of learned a lot of the methods currently used are very traditional. There's a lot of cognitive load on the astronauts, and things are just not super efficient. They don't have any visual aid currently. So in kind of finding these problems, we're thinking, how can we design something that'll address these issues? So we have a few like design tenets. Some might call them requirements. One of them being like safety and autonomy. We want to make sure the astronaut feels the ability to do things that they want to do, but also feel the support they need to feel safe. Another thing we're focusing on is visibility and accessibility. Another big thing is also minimizing cognitive load. And all of these principles point towards an assistive design. We want to make sure that the primary interaction is what the astronaut is doing in the field, collecting samples. We don't want them to be super distracted by the panels that are opening up. So we want to make sure that AR and everything that we're doing is secondary to whatever their main task is. So some of the challenges that we bumped into are listed over here. The big one is that the HoloLens has its limitations, specifically like the scene recognition, how much it's able to see, how lighting conditions can really do a deal on how things work in the real world. So yeah, those are some of the things that we kind of were challenged with, especially throughout test week. Some of our next steps that we'd like to explore. We weren't able to incorporate eye gaze like some other teams here, but this is something that we'd really like to try. It'll really take the load off of hand gestures, even voice commands. The idea is like maybe they could hover around with their eyes and click with their voice. So that's something we'd like to explore. We'd also like to explore navigation in other lighting conditions. So maybe what happens when there's absolutely no light? Like what kind of system do we have there? That's something we'd like to explore as well. And we also just like to do some more user testing in general. So our kind of vision for what we see, maybe this kind of a system would look like. We think that some sort of like display system on the suit should be able to accommodate more or less information. So depending on the mission you're on, the task that you have, whether you're doing geosampling, maybe you're mostly on a rover, we want the design to be able to expand to include more information, and also like be able to shrink and be simplified if you don't really need it. So having a flexible design system is something that we see that is probably going to be in demand. So yeah, you can probably read the rest there, but that's kind of our vision for the future. This is our team. 8 of us are here right now. But yeah, we have a lot of multidisciplinary working together. So kind of hard to coordinate there, but pretty cool. And yeah, that's all from us today. Thank you, and any questions?
Hey, thank you guys. I really liked your video because that showed me exactly from the user point of view what you were doing through a couple of different tasks, and it really got me the sense of how somebody would interact with your device. So great job on that. Just a couple of questions. I also like the way that you've thought about comm, and that you have multiple different comm paths. I think one thing that might be helpful for you in the future is that when we do comm on EVAs, we generally have a very standard kind of aviation, who are you calling, who you are. So I'll always say, Houston Station if I'm on ISS, or Houston EV1, or if I'm talking to my buddy, hey, EV2, EV1, or probably, hey, Ike, it's Kate. So it's a very limited set, so you could probably with 10 different specific words capture all of the communication paths, and that might help you recognize, hey, I want to talk to the device. Oh, now she's talking to mission control. The other thing too is I think I like the wake word. I think you might want to make it one word. Just Vega, and if you're having something where you're going to do a lot of communication, instead of saying the wake word every time, you could say the wake word and then have an end word. And so you know that you're going to be talking to Vega a fair amount, and then, okay, I want to talk to mission control, so you say your end word, and it knows not to be listening anymore, and then you say, Houston EV1. So that these are details that I don't know you could find out really in research, but I really like the direction that you're going with. And I think that thinking about, there's going to be a lot of comm on the moon, and thinking about how we're interacting with our device, how we're getting information done to the scientists, and then how we're talking to our buddies is really important. And then the last thing is the Find Your Buddy feature is great. I really like that. I like the navigation. And the way you talk that was how we would talk a crew rescue on board. I think if we could get his vital or her vital information, that would be something that would be great to see. Anything about their suit or their vitals that you're collecting.
Wow, those are a lot of great comments. Yeah, definitely something we'll look into. Yeah.
I have a question about Vega. How do you see Vega evolving with your design?
So, evolving?
How do you see Vega evolving, or the capability of Vega evolving?
Yeah, actually, to add on to the wake word, that's I just kind of gathered my thoughts, but right now, we do have a 5-minute latency period where once you say, hey, Vega, it's activated and it's listening, so you don't have to keep saying it, but a stop word would be very interesting, and I think a way we could expand on it, maybe Hank, if you want to talk a little bit about the potential.
Excuse me. Yeah, so what we wanted to initially do with Vega was make it much more flexible, and then it can kind of just figure out what you're saying from I guess what you're saying. But we ended up scrapping that because we didn't have enough time to do it since we had a pretty new team. So what we ended up doing was we just kind of hard-coded some commands into Unity, but in the future we want to make it a much more flexible system to use.
Great job. To kind of add on to what Kate said, you can also, a lot of times when you're using your wording, you can have it look for how you mean things. So looking at speech to text and how that translates and how it can start to understand how you mean things. So if there's certain phrases that mean something, you can have it. It can also take your iteration and how your emotional level. If someone else is saying something is, I think what was it, Joey on Friends, how you doing is lots of different contexts. So how you mean it, the level you're saying it can all have some meaning. There is a lot of work that we're doing with AI and ML into HoloLens. I know that even at a product level, I know they're working on it. I also know that in individual projects, like projects I'm working on with NASA and with NOAA, with certain areas, that we look a lot upon that. So I think you guys are really going in a great direction there, and I loved that, and I'm excited to see where you go.
Just a quick comment. So I was lucky enough to be your test subject last night, so I will agree with Kate completely. Had a blast with you guys, and it was really intuitive. I liked it. One of the features I really like, interestingly, is your navigation aids that are always pointing home. As Kate said, the moon is pretty featureless, and if you've done much scuba diving, it's really easy to lose situational awareness. It's kind of nice having a simple feature that's pointing back. If something goes wrong, that's where I need to go. It was subtle, and it was really nice. Even though I wasn't in a hurry to get back to the lander last night, just having that there was kind of a nice feature that I liked.
Sometimes when it's dark, it's hard to get back to the airlock. I think one thing that may help you out if you're interested in kind of exploring these compass is you can just listen to audio from station EVAs. So, our most recent one was EVA 80. You can listen to EVAs, I can't remember which one I did. 76, I think, might be a great one. They're long and they can be a little bit boring, but you can hear the cadence of the crew members talking to each other, and you can hear us talking to mission control. We don't have any devices to interact with, but that will give you a sense. It's pretty, if you do an ontology of the language, it's fairly limited set of vocabulary of things that we're going to be talking about. And I imagine on the moon we're going to take that, this is kind of how NASA has always communicated. We'll take that as a communication standard forward.
If you do go the path of natural language processing, I would just be very selective about what type of libraries you choose for. If you do some sort of audio analysis, so just kind of understand what your requirements and priorities are from that audio analysis, and then choose an NLP library based off of that. Just a suggestion for next year.
These are all great suggestions. Thank you.
Great job. Thanks.
Thank you for having us.
And at this point in our program, we have a stretch break. So we're going to take a stretch break and be back in about 15 minutes. Welcome back, and we're ready to go with our next team, which will be Team Alexi, Embry-Riddle Aeronautical University.
All right. Good morning, everybody. My name is Graydon Russell, and this is our team from Embry-Riddle Aeronautical University, and this is Alexi 3.0. So the problem we are seeking to address constantly is providing crucial information for astronauts on lunar EVA. This means that we have to constantly be considering all of the unique challenges that come up with this setting, including the harsh working environment, the limited mobility caused by a pressurized suit, and the limited space available within the suit visor. We set an overall goal for ourselves of just helping promote autonomy for astronauts, making them independent from mission control, being able to function on their own. And we find this very important as more and more astronauts will be venturing further and further into space over the coming decades. And so to do this, we provide suit and crew vital information. We look to help in search and rescue capabilities when they arise, and we want to provide navigational and procedural references. So, an overall design philosophy for our system is to emulate current real-world EVA technologies. Primarily, we like to focus on the XEMU suit, and so we designed our system to simulate the built-in suit displays to imagine basically each screen is a physical display on the visor, whether that's inside, outside. That way it tracks to the torso motion and you have free range of head. Additionally, we use a hardware control scheme mimicking the DCU on the XEMU, as Miranda is demonstrating right here. And so we just have a simple 2-button control scheme using the head tracking as a cursor. And lastly, we utilize predetermined site maps, not pre-scanning with our device, as we wouldn't be able to walk the site prior to an actual EVA. And so this is Alexi as it currently stands. It is a 2-screen system with our persistent vitals on the user's left. Meanwhile, a app system with several different applications for the astronaut to use during EVA on the right. Additionally, we have some navigational aids throughout both above and throughout the world in front of the astronaut. So for our navigation, we have a 3-pronged system. This is to provide redundancy, and the astronaut is able to choose how they would like to navigate. First off, we provide an auto-generating 3D path that moves around both predetermined obstacles and live updating as it scans. Additionally, we have a compass system that is always floating like a halo above the astronaut. This includes waypoints and numerical heading information. The waypoints do include distances, and they are falling waypoints, and so the closer you get, the lower they go on the horizon until they touch down at the actual location. And lastly, we have an actual navigation screen in our app system where we provide both local and global mini-map systems, which include all of our waypoint markers, as well as distances to the markers and estimated ETA. Also within our app system, we have a couple others. First off is a task application. This provides step-by-step instructions for the crew. When this is in a predetermined plan for the EVA, we have shortcuts that help the task screen basically go step-by-step, connect you straight into your navigation, straight to your science sampling screen, whatever it is. Everything flows one to the other in your predetermined EVA plan. Meanwhile, in our science application, we have sampling instructions and scientific reference materials, including images of past samples, video logs, voice logs, things like that. Meanwhile, on our left side, where we have the vitals, vitals will stay up pretty much through the whole EVA. However, we do have some additional options, including a telemetry stream settings option, as well as a screen for system settings where the user can configure certain settings to their liking. including flipping the screens as both of the screens are off to the user's side. And so we found through human-in-the-loop testing that after a few hours of constantly looking side to side, your neck starts to strain. And so if you're always referencing one side, you can just flip it, and now it's on the other side. And so here is a live demo of the system in use from, I believe, yesterday morning, possibly 2 days ago. So you can see here's our vital screen off to the left. Meanwhile, our navigation app on the right. We have a return to lander button in the middle there. And then there's our compass with all of the waypoints currently displayed. And there's the path generating out in front of us with little waypoint markers off in the distance indicating different locations. It was a bit quick there, a bit jittery due to the recording, but we do have a main screen that floats in front of the user at all times that provides limiting factor information as well as the current mission time. And should any emergency warnings come up, they will pop up directly in front of the user at any time. And that is, oh, there we go. That is Alexi as it currently stands. Thank you very much. And I will hand it off to Mike to guide our question and answers.
I really like what you guys have done with the navigation. It's very thoughtful. I think really a great strength of this. I am a fan of the line on the floor versus things overhead, but you know, ask a different astronaut, you'll get 10 different opinions. But I really like that, and I like the compass and the fact that the waypoints are dynamic, because you may be walking along and you might change your plan in real time based on conversations with the ground science team, and so this kind of it gives you a lot of essay about where you want to go without having it be too cluttered. I like that target overview map, but that's off to the side. So I think you've just done a really superb job with the navigation. There's nothing in here that would irritate me, and it's like all the stuff I want. I think on the vitals, that's great to have as well. I would suggest maybe a couple of toggles with how much information you're displaying, so that you could have, because there's a lot of words on here, you could have something where it's just like green, everything's green. Hey, I want more information. It goes to like the actual numeric values of everything, and hey, I want even more information. It's got like the log history of previous, caution warning messages or something like that. So have a few different layers of how much information I want displayed at a time. And then I think I've seen in a few others too. For most of the data, I probably only want one significant digit. If it's two, then it's just too many numbers. So, and the UIA, you want that when you're getting to the airlock or you're doing a repress or a depress, but when you're out on your EVA, you probably don't need that. So kind of popping things in and out of that spacesuit vitals display will clean it up a lot. But I think the navigation is just beautiful. Thank you.
Thank you for the considerations.
I also really like that you have it so you can flip sides. So if you have someone who prefers it on one, you can do that. But I like that it's also turning to the side. It's not always in your line of sight. So if you need a clearer picture, you can see that. You're a smaller team than some of the other teams. How did that work for and against you? And then also kind of what were your big lessons learned and I'll say goals moving forward?
Just to talk about the swapping, Graham did mention we also have a scout mode where if you're just looking straight, you double tap on the trigger. Everything is gone except for your compass and navigational aids. So if you want all your whereabouts while still maintaining navigation, you can. So regarding to our team, Alexi has been a 3-year iteration. So like our requirements and our teammates do change over like when students like graduate. So these are two newest members like Joe and Miranda. So we always try to do good documentation and fill them into the loop and do as much communication as possible. We have prior teammates that have also like software, HF backgrounds who have also had internships without the aerospace industry, where we always try to take in consideration what are the limitations of like being out on an EVA, how can we make it grounded, how can we solve problems, because like we know like the spacesuit is limited, especially when it's pressurized, so we want to make it like, that's why we use the bumper and trigger, for those aspects. We don't really rely much on like gestures or eye tracking to do those type of feats.
Have you considered adding voice commands to change the screens opposed to the human in the loop interaction where you can have fatigue with the human?
Yes. So we actually don't use the Microsoft HoloLens. We actually use the Magic Leap headset. So the Magic Leap headset has limited API capabilities. It's not as wonderful and like with all the libraries and packaging that Microsoft provides with the HoloLens. The Magic Leap is its own operating system. It doesn't recognize anything that's Microsoft, sadly. And this system is actually kind of old. It's 3-4 years old now. So they're coming out with Magic Leap 2, and we're noticing things are becoming more standardized now in the AR industry. So we'll probably be able to use some of, hopefully, those Microsoft tools to integrate voice commands. Right now, the only voice commands we have is taking video and photo. We've had like workaround and thoughts to maybe do web requests of sending what we're saying and then receiving it back as an alternative, because we can't really build, like, it doesn't recognize what Microsoft like is or any other libraries that we would choose, because the operating system is so limited, because it's called the Lumen operating system that they use on the headset. But we have taken that into consideration.
So my question is kind of alluding to some of the Magic Leap limitations that we saw. So I know that we tested in the daytime, but one of the things I appreciate is kind of the chest locked component you have, and it gives you head-free capability to move around as well as the compass heading. Is there a plan to move to a different kind of environment? I know there was quite a few limitations, so what are kind of your thoughts on that?
Yes, we do plan. We really like the remote and the capabilities that it brings to us, because we can mimic, what we believe NASA's working on at XMU, having stationary possible screens. It also allows the head to be more freely versed. So we do plan on getting the Magic Leap 2. I don't think all the information has come out about it yet, but we believe it could be able to help us better in like your lunar environments. It works really well during the daytime. That's why we have like 3D printed visors that we can put on and off the headset to make the visuals more appealing to the user. But we do plan on getting the Magic Leap 2 and seeing how that works. The Magic Leap 1 has IR, so it does depth tracking, which I know is different compared to the HoloLens. But that's what we are working with the limitations of hardware. So,
can you speak a little bit to how you define your path and what maybe algorithms are feeding that information?
Yeah. So the way we do it, so we have a 3D. So from Google Maps, or Google Earth, we get the 3D model, and we have it loaded into Unity. And so what we do is we have I know you heard other teams called a nav mesh. So in Unity we have a nav path where we then have, this is like a mountain, so we'll determine that's like a slow speed, and we have craters that determine slow speeds, and we get your GPS signal, and whatever the GPS signal is. This was actually one of the challenges, is lining up the real world and the game world together in real space. So to make sure our rotation is correct and our position is correct, that was one of the major challenges. But to do that path, Unity provides us AI tools that calculates paths given obstacles, and we actually have that live. So the Magic Leap has, I've noticed if you saw in our settings, we have obstacle on and off, or occlusion on and off. Occlusion allows you to see the path through obstacles. If you shut that off, then you can't see the path through obstacles. And then obstacles allows you to see also what Magic Leap is scanning. So Magic Leap can determine rocks that are on the floor, or ceiling, or walls, or doors. And we just add that into our mesh, and then it just updates the path along. It's a combination of both live and offline, if that answered your question.
Yes, that's perfect. Thank you.
Okay, thank you.
That's all I got. Thanks,
okay,
guys.
thank you.
Great job.
Great job. And next up, we have Team Cutie from the University of Colorado.
Oh, yeah, thanks. Hello, we are the CU Technology for Extreme Environments team, and this is our exit pitch. I'm Sydney, this is Addie, that's Ian and Freddie, and we'll go ahead and get started.
So first, we're just going to talk about, I guess, what features we have. First is our vitals. As we know, this is data collected from the telemetry stream. It gets sent to the user, and the user can say, okay, is my O2 good? And they can just monitor that throughout the EVA. The second that we had was notes. This is note-taking capability for when you're actually at the site, and you say, okay, this is an interesting rock. I want to save this information. Maybe put a waypoint down. Our third component is our navigation. So we have long and short-range navigation. Our long range consists of visual waypoints in the distance that the user can navigate to, and you'll have like a cube that you can sort of follow around that'll guide you to that long-range waypoint. And our short-range navigation is just the wireframe that the HoloLens scans. And with the wireframe, you can see closer-range obstacles. I think in the bottom right, you can see this backpack that's sort of been highlighted for the user to, easily observe. It's a little bit harder in the dark, but yeah. And the last one is the Lunar Search and Rescue. So when we receive a message from LSAR, we can, look at it, find the coordinates, put a waypoint down, and reply back. Yeah.
And to expand on our software results, here we have two images showing more of our capabilities. So in this top image here, we have Lunar Star notification coming in, and so we can send and receive messages, and luckily we were able to complete that during testing and have no issues with it, so we're really happy to have that. And then on the bottom, we're showcasing our navigation capabilities with the waypoints, and so that blue line in the background is an example of one of our beacon waypoints, and so they extend high into the sky for maximum visibility, so wherever you are, you can see them, and so that astronauts can always have that waypoint when they're navigating around the moon.
All right, and then our team decided to integrate a peripheral device, which was an electromyography sensor. And so the objective of that is to be able to communicate with the interface hands-free, and also it helps negate the clogging of the communication lines by doing voice commands, and then also it's difficult to be doing hand gestures in the dark, we found with the HoloLens as well. So how it works is it would be the functionality would be turned on just by a single voice command on and off, and then during the period when it's on, you can use it. It produces analog values that's proportional to the electrical waves produced by the muscle, and then that there's a threshold that we put on the sensor, so you can communicate regularly still with the other astronauts during the EVA, and then it won't trigger the sensor unless you've actually flexed the muscle hard enough to produce a high enough number, and then that would allow the cursor that is paired with the electromyography sensor and eye tracking to be engaged through the system. And so we have done human testing throughout the year to decide where to put the sensor and how it can best be used. And so we tested the forehead and cheek and neck to place the sensor, and we found that the neck is just awkward, uncomfortable, it's inaccurate, the muscle fatigues easily, and then kind of as well with the cheek, it's kind of in the way of eyesight a little bit. It's still awkward and inaccurate. So we decided on the forehead as the best place to put the muscle sensor, and also it's very easy to raise your eyebrows and communicate or allow the sensor to communicate easily then. So we found that it is the most accurate as well when communicating. And so that's how we chose to use the forehead muscle as the correct placement for our EMG sensor.
So just some of our challenges, successes, and future plans. Some of our biggest challenges this year ended up being a little bit more organizational, with a pretty big loss in team members at the beginning of the year, and then also losing most of the code base that we had from 3 previous years of this challenge. But I think our team worked through those challenges really well to get here today. We had some really big successes this year, one of which being we were able to get funding to purchase our own HoloLens so that in coming years we'll be able to use that and start development much sooner than we were able to get to this year, as well as rebuilding a significant portion of our code base when we lost it, and then getting to human factors testing with our EMG. Our EMG has been something we've worked on in the past, but never been able to do human factors testing with before. So we've really gotten some good data from that and feel like we're heading in a great direction with that technology. As far as our future plans go, one of the big ones is trying to make sure that our team all has the same or is on a similar level of ability with getting this work done. You know, we want people to be able to come into this group without the skill set and gain the skill set. And so things like coding workshops where people can learn, and then also looking at doing some off-season development with getting the rest of that code base back up to where it used to be, so that starting challenges in the future years, we can start off on a great foot. And then finally, in the future, looking towards that EMG sensor becoming more of a complete product, with it being integrated into an easy-to-use, easy-to-integrate headband, something that could be added to auxiliary components that are already used in the suit, and things like that. So, thank you.
What made you guys lean towards the EMG? I mean, I love it. I'm for it. I mean, we do sensor work. I know there's a lot of other companies/countries that are doing sensor work right now for other agencies and for NASA. And I know there's even, I know DoD is looking at things like that, wearables and how things are functioning. I love it. I think it combines a lot of information into one. And what made you think of it?
It came from a couple of places. One of our mentors, Dr. Anderson, does a lot of work with wearable technology, so like textile electrodes and things like that. And so she had pointed us in that general direction when we were talking to her about wanting to really focus on the hands-free aspect of this. And then just for a couple of us through our jobs, we're familiar with the comms being clogged issue, and wanted to avoid that being our solution, since we work with that on a daily basis and didn't want to design towards that. So we were looking for something hands-free that you could use a different part of your body, so essentially a different muscle, and our advisor had suggested we look into it.
One thing I would recommend for the EMG work is that there is a study out of JPL where they used EMGs to control a robotic arm for robotic arm manipulation. And so have you gotten a chance to do any literature review on it?
We have not. So this is something that's been in development for a few years.
Yeah.
But with this year, we're all new.
Great.
So.
Yeah, I would just recommend, maybe a quick Google search, or if I find it, I might send it over on Pronto.
Yeah.
There's a lot of learning curve there, but I think that threshold you set for the muscle activation is going to be pretty key, and making sure that nothing is actuated outside of that threshold, and kind of doing some user testing on that. But other than that, I'm really impressed with how you guys kind of came together on the last day of testing. So I know you guys had to overcome a lot of challenges, and I just want to commend you for getting the Lunar Search and Rescue working and being able to send messages back, and then also being able to navigate from point to point. So great job.
Thank you.
Yeah, I really like this because it's creative and it's, solving the problem in a different way. So, these kinds of things are really good, because sometimes at NASA we get very focused into the way we've built something for a long time, and so I love these new ideas. So kudos to you guys for just thinking of something out of the box. One question with the tunability is that you may want to think about having it be individually tunable, because we, hopefully at some point we'll send a lot of people to the moon, but in the early days we're going to know exactly who's going, and you'd have access to them, to make sure that it's really for each individual, because you might have different forehead muscle strength. And then the other thing to think about is how does it handle sweat? We get EVAs are hard, and like I can take my socks and like wring them out after an EVA. So we sweat a lot, and then I don't know if you thought, but we will have a high oxygen environment in the suit. So making sure the electronics are all compatible with that suit environment. There's a lot of regulations about what you can put in an oxygen environment. So that's something to think about since your control is not an externally mounted. In some ways, it might be an advantage because you don't have to deal with vacuum, but you will have to think about the O2 environment in the suit.
Thank you.
Yeah, to Kate's point about the tunability, I think one other thing to consider that was a kind of lessons learned from the paper was muscles under fatigue. And I don't know if maybe all of us have experienced this in the past week where we haven't slept and our eye twitches. And so there are some like involuntary movements that can happen that will incite the EMG when you don't intend it to. So yeah, some thorough user testing would be great.
Yeah.
And that's all we got. Good job.
Great job. Okay, and our next team up is Team Moonbuddy with Carnegie Mellon University. Just be mindful of your camera over here.
Okay. I'll help you to control.
Okay. Hello, everyone. We are Team Moonbuddy from Carnegie Mellon University, and we'll be presenting our augmented reality solution for navigation for kind of lunar stuff. Oh my God.
It's okay.
Lunar navigation. There. So this is our team. We are an interdisciplinary team from multiple departments. Many of us come from the School of Art at CMU, as well as computer science, information systems, and human interaction. We're a mix of undergraduate and graduate students.
Hey, Moonbuddy. Start mission. Open task list. Next task. Close task list. Go to station A.
Moonbuddy operates on three main interaction components: our voice user interface, mission task list, and real-time navigation. So for our VUI, we were primarily interested in how astronauts might have difficulties in using gestures in the moon. So you have this really pressurized suit, and you might not have a lot of autonomy in being able to move and kind of do this. So we put on gloves, tried doing a lot of the interactions and feeling that, and we noticed that the activation was really poor for that. So we thought it might be interesting to actually approach this challenge using just voice user interface interactions. Similarly, we also have a mission task list structure so that the astronaut can reference the tasks that they might need to do, especially for geology tasks. So obviously we're going to have a really trained person that's familiar with this when they're kind of doing this in the moon. But we thought that kind of for the purposes of this challenge, we also don't know how trained the person might be and if they want to reference kind of these elements of the task list structure. So we thought it'd be interesting to have something that they can reference. It doesn't have to be referenced at all times, but if they need some information, they can easily retrieve it. Lastly, we have real-time navigation, kind of a working map and compass that allows astronauts to be able to figure out and kind of locate themselves within the lunar landscape. So now, this is a little bit kind of an overview of kind of what the basic interface looks like. Kind of this is when everything is sort of collapsed. You kind of have to look upwards to see some of the references for the voice commands that you need to see. But other than that, everything is collapsed and designed so it's not obstructing your field of vision. Now we're going to talk a little more in depth about what each of these individual components do.
Right, thanks Angie. So let's walk through how all these components come together with those three interaction
concepts that we talked about in fulfilling the EVA mission. So the first component is that mission task list that Angie has talked about, right? We really wanted to reduce the cognitive load of the astronaut in space on the lunar surface in remembering all the instructions that they have. So while these instructions might come from mission control, we also have baked this into the display. So you can see the current instruction of which station you need to go, or specific reminders about the geology task that you're doing. If you're new to geology as well, you can have an expanded display of this task that might remind you what are the things you might need to describe for a rock or regolith, and the voice commands that you might use to trigger that recording of a photo in front of you. So you can see the expanded mode on the screen above right now. Most of these components can be expanded or collapsed to display more information or get out of your way when you're done. The second element, of course, is the EVA Vitals. All right, like many of the other teams, we also display the current set of consumables above, always available on the display. But when you need more information, you can expand to see the meters for each of the individual resources, and also see if they are currently in range, and there are color-coded warnings if they happen to get out of range as well. So now that you have all the information available, you need to get to your station, right? So we are providing a few different means of providing navigation guidance on the lunar surface. The first is the compass you see on the top, right? As you rotate around, the different stations and their positions are displayed in front of you. So in order to get to, for example, station A, just have it in the forward view of your current heading and just walk forward. As you move forward, the compass indicator grows larger so that you know you're getting towards that area as well. And to also help you to establish your position, there's a live map that we display your telemetry server position on there, and it constantly updates as you move around so that you can get a better sensing of your environment as well. So on the lunar surface, we want you to remain safe as well. And here's something unique that we have done. Based on the spatial mapping data that comes out of the HoloLens tool, we have applied a custom shader that does edge highlighting of different edges of any protrusions or depressions in the ground. So in this example over here, you can see that this couch is very poorly lit in the environment. But with our edge highlighter, it actually displays the actual edges without providing too much information, such as difficult to see where you're going as well. So we think this is will be very helpful to astronauts on the surface. All right, and when you do get to the station, now it's time to perform that geology task. I already mentioned that we provide prompters for anybody who's not familiar with the look-out process for the geology process, and it really takes you step by step in describing all the characteristics that you need to do. Of course, you can also record photographs by just saying record photo, and you can just hold the sample in front of you and trigger this hands-free. And lastly, our system's also hooked up with the Lunar Search and Rescue Protocol. We do display the Lunar Star messages that come in and allow you to respond as per the protocol, and also display these Lunar Star coordinates on the map and compass, as you've already seen. So I hope you are able to see how this interface, while it's simple, allows you to get to all the different functionality just by using a voice and just by speaking to MoonBuddy.
Awesome. Thanks, Ron. So for our testing, we did about 10 testing sessions throughout the development of MoonBuddy. We interviewed people ranging from novices to experts in the field of geology, AR, VR, and field research. And with that, we were able to, with the feedback and criticism, we were able to fine-tune MoonBuddy into the effective interface that we present to you today. Perfect. For our most recent rock yard testing, we are actually over the moon, pardon the pun, with our outcome. Basically, with our test participant, she essentially said that our interface was extremely easy to use and extremely easy to navigate and very intuitive. She also explained that it's very easy without formal geology and navigational training to use MoonBuddy and just be able to really navigate it easily. Yes. And then for our outreach, just kidding, yeah, outreach, we did about 4 activities. And within these activities, we ranged from K through 12 students to undergraduates. And each activity varied depending on the age, but the emphasis was on allowing them to explore the development of Moonbuddy, as well as understanding the HoloLens. And then we also emphasized curriculum activities for hands-on coding and interactive workshops for younger students using Littlebits, Code Kits, and MacBook Airs. So we were extremely happy to bring that to our community, and especially for our outreach, it was really great. So then just kind of finally, as a final note, we are so thankful to be here. So thank you so much for the opportunity to come and present to you all at NASA. We are so excited to be here. So thank you again.
Couple things, comments maybe for some of the other teams too. Whenever you have, one of the things I really liked, when you had an emergency, when either it's a consumable that's past some point where you're in trouble, want something that's really visual, that's in your face. Remember, the crew members are really distracted doing what they're doing. So I like that. An audio accompany with that's probably a good thing too. Again, you really want to get their attention if it's something that's at that level. So I thought that was really nice to see. This edge highlighting thing is really cool. I'm starting to think as we look at the environment we're going to at the South Pole, it's really, really dark. And so I'm starting to worry that it's not as simple as just slapping more lights on the crew member. Even as we were practicing out at the field, you know, you turn and look at your partner and they're blind. And so that's going to be a problem. And so I'm starting to think that it's not as simple as just lights. We're going to need some other tools to kind of figure, and that's really cool. And so I think that concept is really neat. It'll be interesting to see where you guys can take it and get us thinking about how we can deal with it too. So.
Thank you.
Yeah, I think the way you've done the warning messages is really good because the text is not too small. It gives me all the information I need. That we have a problem. It alerts me boldly where the buddy is. Things like distance to the person is really important. I think an arrow marker, because like this kind of thing happens, and like in an airplane we call it a wait on butt switch. Like you just don't have a lot of thinking capacity when you're in an emergency, and so this information is everything I need and nothing I don't, and then that ability to immediately respond is super helpful. That would just like get you right on your way with no processing from the human that's needed. So that's really great. And I second Chris, this edge detection thing is really awesome. I think we're going to have a lighting solution, but we also need some software solutions for recognizing obstacles and changing lighting conditions. So super cool and really innovative. Thank you.
Thank you.
I third Chris and Kate's sentiment on the edging detection. I actually had a chance to look at it with my 10-year-old when you guys were doing your poster presentations, and she thought it was cool. I'm curious to know, with regard to your education and outreach initiative, how was that received, and how did you blend the HoloLens into the simpler concepts that you were teaching them?
Yeah, perfect. So with outreach, especially when we did, so it ranged from what kind of age the student range was. So for younger students, like K through 12, specifically middle school is what we visited with Comet. We emphasized first talking about Moonbuddy, exploring the development, allowing them to understand a bit about what we're doing here with NASA. And then we went into, okay, here we're gonna teach you a bit about how to code and make. And we used these kits called Littlebits, which are essentially, I'm not sure if you've heard of them, but they're little modular electronics that snap together. And it's a really fun hands-on learning activity, and it really allows students, especially 4th and 5th graders, to get really excited. So that's kind of how we blended it in with that way, and essentially we built Moonbuddy. Here's how you can build something hopefully in the future similar to that. Yeah.
I'll fourth everything. I do. I love the edge display. I think that's important. I think that actually I think a lot of technology that's coming out right now will be with things like that, and with things like stealth radar and sonar and whatnot. So I loved that. I loved the pop-up, like everyone else said, being able to know, because when your head's down looking at something and you need something to catch your attention, and I think it was good. I also liked that on the compass above it, it showed you where they were. So if you're facing a different way, you get turned around easily. I loved that. and I really like the outreach, actually. I know from us, from a different kind, we're not an agency, we're a company, so being able to work with people to help them learn how people can be involved. A lot of growing up for myself, you thought that only astronauts would be able to do certain things. Now we're finding out that, doctors are holoporting to the station, and anything that you do can have bearing on the space industry. And I think getting out there and getting to kids early to show them that is very important. I thank you for doing that.
Thank you.
Awesome job on edge detection. I think your compass heading was also something that I wanted to talk about. When I first saw it, my initial reaction was, is that a timeline? And then my brain went, wow, what if we did have a timeline kind of heading where you were walking through and everything that every action you had just taken had been placed within that timeline. But then there's also this importance of also having your heading and your compass direction. So my misunderstanding of your heading kind of gave us some unique ideas there, but so just a comment on that, maybe looking if you're intending for that to be a heading direction, then maybe have some different iconography, do a little bit more user testing, maybe look into some of the UX elements there. And then I also wanted to commend you. I think we're all excited about your edge detection case, but beyond that, I think for everyone in the room, every year in August, we send out the mission description. But I think one thing I would give you a challenge to do is before you even take a look at the mission description, just don't read it first. You have to read it before you come to the challenge, but before you start planning what you're going to do with that mission description, what you did was not really a function of the mission description, but it was something that immediately aided the goals of that mission description. So I would just take a step back, really understand and talk about what it means to do an EVA. If you have opportunities or moments to interview somebody, do that. But also, YouTube is a wealth of knowledge, and just take some time to watch EVA videography and really understand what happens end to end and how you can make that better and what magic use case would make that better. And I think that's kind of what everyone got excited about with your edge detection. And so, for any teams that are planning on coming back next year, really take that moment to just imagine and make believe and play pretend, because ultimately when we have, with tools like machine learning and in the software world and in AR, it's literally magic, and you're creating a virtual world that overlays on your real world. So just take that moment to be creative and step back before you start planning next year, and I think that's kind of what you guys got to, so I appreciate that.
Thank you so much. Thank you.
Great job. Thank you very much. All right, and now we have Team Arrow from Stanford and University of Southern California.
Awesome. Hello, everyone. We're Team Arrow, stands for Augmented Reality for Roaming Off-World. Totally a case where we came up with the acronym of the word first, then came up with the acronym. My name's Arjun. We've got Rylan here, Neha, Matthew, and then a fifth team member, Karthik. We've got a better slide for this, actually. There we go. Who had to fly yesterday. But this is our entire team. We're from Stanford and USC. And kind of the outline of what we'll be talking about is kind of a quick walkthrough of our overall UI. Most of it addresses the immediate mission briefing. Then we'll talk about some of the elements that we wanted to try out, such we thought were unique. And then we'll talk about a lot of the lessons we learned over the past few days. So I'll pass it off to Neha to quickly walk us through the UI.
Yeah, so we have our overall UI over here. Our main interface kind of composes of two main parts. We have our persistent information, which has the display of the vitals and also an overhead compass. And then we also have a diegetic hand map, which is able to come up and down as you raise your hand. And then we can go into the next slide. And for our geology module, we have the ability to pick up a rock and put it in front of you and sort of measure it with different dials. We can also record different properties about our rock. And then we can also match the color of the rock using different sliders, so we have a very accurate representation and measurement of the rock. And one of the main design principles we kind of want to have throughout the entire thing is just a multimodal interaction, because you never know when you need your hands and when you only have your voice to speak. So we have voice input and touch input.
All right, and so what aspects of our design do we think worked really well, and how did these play into our design philosophy? So one of the key concepts that we had was to keep the interface minimal, so not obstructing the astronaut's field of view. And one of the important ways that we did that was to have the only persistent elements of the navigation or of the interface in general being this persistent compass, which is over your head. And then if you have a target in mind, then that target appears locked to the compass as just a small arrow showing the direction and the range. And then as you get closer, well, if the target is outside of the field of view, then the arrow changes to show you which direction it's closest to. And then as you get closer to the target, that arrow will drop down into the environment around you so that you can see exactly where you need to go.
Awesome. And the other element that we weren't sure if it would work, but we're really interested in exploring, because the HoloLens enables this, is the idea of anchoring something to your hand and having your hand be your main way of opening or closing the UI. There's a couple of reasons we did this, but mainly it's because it's very intuitive and it's something astronauts already used to do. The kind of cuff checklist is something we learned about. It's something that's used a lot. So basically, this would be adding no new persistent element to the UI. It would be something they're already used to using. It can be waved away because you can just put your hand away. And so that's something we were really excited to play around with and we thought worked really well when we were testing. Cool. And then the last section is we've got kind of a rock air testing. We've got some pictures here with our evaluators. But then I'll pass it over to Rylan to talk about a lot of the lessons we learned.
Thanks, Arjun. So we made an AR interface for space, and this is the turning point. Where do we go next? So we learned that the hand map is kind of a core part of how we navigate around the moon, and so consistently having it available on your hand can actually tire out your hand. So we're thinking, how can we pin that to your vision? And then also, lighting is a huge issue on the moon, especially at the South Pole. So, some kind of different external lighting system, as well as, this is really meant to be a very quick way, a quick alternative system to navigate instead of a compass. And for generally, our core UI design philosophy is really about having a fallback UI where we have multiple UI systems that can all do the same thing, but in case, for example, a telemetry fails or something else fails, we always have a fallback to a different interface. It is adjustable. You can customize it so it's custom to the user. And other things like voice control can also enhance the experience where other UI might just fail at certain points. So we have to plan for every single possibility that might come up on the moon. And also, we have a principle of a minimalist UI. We don't want to distract the astronaut from anything, that they're in a very cognitive load, a very high cognitive load situation. So we want to highlight the very important aspects of the UI and minimize the other ones so they can really focus, heads down onto just, repairing something or saving one from something, and also favoring visuals and icons over text is a very important aspect of that as well. Wait, next slide. Oh yeah, so we really want to put AR on the moon, arrow on the moon. So there we go.
Great job, guys. While I like the hand map, I think it's very intuitive. I think it also, you should definitely work on a way for it to just be pinned off to the side. A lot of times you're not going to have access to use your hands. If you're using both to do one thing or something else, you can't necessarily do that. So that's my biggest feedback. Other than that, I think it's great. I love where you're going. Thank you.
Hey, I really like your focus on minimalism. I think it's something to pay attention to because we do have a lot going on. We've got an audio stream coming in. We're like looking for the right rocks. You know, where's your buddy? How's my suit? Where am I going? And so the design of your minimalist system was beautiful because it was really paying attention to the key things that we needed and not the stuff you don't. So things like I really liked your vitals were just icons. There was no text that I had to read, and they were big enough that I could see what was going on, and then it was color-coded with criticality of the system. So that's an example of having a lot of information in a very simplified rendering that tells you what you need to do. I really like that. I like the hand map too. I think that's one of the ways to solve, I think in the gloves we're going to have a hard time pointing at things. Like this is basically, you can't do it in the gloves, but I can bring a flat palm up. I think we are worried about making things hands-free, but just in my experience of, I did a bunch of field geology with ESA last summer, and you're doing tasks in different areas. So you're either navigating, where then you do want to bring things up, or you're stopping to sample. When you're stopping to sample, your hands are going to be in the tools, but you don't need the map at that time. And so, it's very rare that then you're taking pictures and documenting your sample. That's where you do need like a camera feature or those measuring features or something like that. So you may not, you may pin your hand map when you're mapping the sample and then use various things. I think a lot of people have talked about how difficult it is to work in the suit and the gloves, and that's a really good thing to think about. Hopefully our new suit's going to be a little bit more flexible, but paying attention, like maintaining a body position is very difficult. I think for the pointing issue, one thing we could think about is you can just point with like all fingers together, and so if you can capture that as a point and this as a hold, that seems like it would be a reasonable thing. So I think you've done a really good job about thinking the limitations in the suit and what is going to be totally intuitive for the human without overloading them. So I really like this.
Thank you so much. It's great feedback. I think one thing for the vitals, one thing we realized early on is, like a principle usually with UI is you want to make sure that any user, regardless of their background experience, can kind of understand what's going on. But at least with this mission, we could circumvent that a little bit, because with the vitals, it's okay if you don't know what every symbol means, because this hopefully is not your first time seeing them. So.
One of the concepts that I think your team did a good job introducing was taking advantage of the three-dimensional space you have in AR. So I think one thing that we really get stuck on when we design human interfaces is we have display standards that have been standardized over 50 plus years. They're, by the way, constantly changing, but the AR standards and VR standards have just been developed on an international level in December of this past year. But one of the what we're very used to as like humans designing for two-dimensional information in a space, and I think with your hand map, you started to introduce what it means to take advantage of the 3D space. I think one of where my brain went with your compass heading was, what if you could tie, I mentioned the timeline earlier, but what if you could tie elements or actions you've taken within your three-dimensional space, and then your compass heading is kind of your center focusing point. You can have maybe like an overhead view that can be pulled up on your map in your hand. And so like my brain just went all over the place, and I really appreciate like what your design kind of introduced to me from a creativity standpoint. So good job on taking advantage of the three-dimensional space.
I can get a rapidly comment that a lot of the HoloLens, Magic Leap, Oculus UI pretty much directly mimicked what mobile and desktop UI already does today, kind of like flat 2D screens, and they just kind of placed it around. And we noticed an opportunity that, especially for navigation, that's a very spatial task, spatial UI if it's a spatial task. So we think that that's one of the main affordances that AR can have.
Thank you for taking advantage of that.
All right.
Great job. All right, and now we have Team Hokey Nuts from Virginia Tech.
Hi, my name is Mithil Atsul. I'm the team lead and lead hardware engineer of the Hokinauts.
Hi, my name is Burak Topo. I'm the software lead.
Hello, I'm Jasmine Walker. I am software.
Hi, I'm Sabrina Lesser, and I'm in hardware.
Hi, I'm Kian. I'm part of software.
We are developing a display called Hoki HUD, and I'm going to take you right through it. And our faculty advisor is Professor Wallace Santos Legis. So here's basically an overview of our presentation. So I'm going to start with the team overview. We kind of introduced ourselves already. Then we'll go through the different design aspects that were new to this year. I'll talk about our outreach activities, our future work, and then conclude. So here's our team. So we have 3 sub-teams. So we're multidisciplinary. So we have a hardware team that worked on peripheral devices that interface with the HoloLens. We have a software team that did the software on Unity. Then we had our graphic design team that did the icons. We're mentored by Rico Acivas, who's the lighting lead here at Johnson Space Center, as well as our previous team lead, Anjali Sapra, who's a software developer at Microsoft.
So this is our navigation capabilities. As you can see, when you click on a waypoint option, a green cube pops up. So in our UI, you'll see a lot of green because that color is very visible to the human eye, so it makes it really easy to see things that are going on. We also made the 3D objects very large so you can see the waypoints from far off, and it works by taking the GPS coordinate of the waypoint and GPS coordinate of the HoloLens that we get through the telemetry server and the phone sending the data, and then it calculates the distance and the heading between those two to put the waypoint there.
So another feature we had was audio note taking. The astronauts can record audio notes and play them as they wish.
Hello, 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 hello.
And this year we added the telerobotic control and science sampling to our project. So the main point of this robotic system is to help in data collection and navigation. So as you can see, we can control the rover from the HoloLens using buttons. And so we're doing this over Wi-Fi on the same network as the telemetry server, which we're also getting data from. So it's and we can take images and send those images over the Wi-Fi connection from the robot to the HoloLens. And we also have a spectral sensor on there that we can send data from, though we weren't able to integrate that with the latest UI design. We also have point and move capabilities for the robot that hasn't been integrated on the latest design. We'll be able to point to a location and the robot will go there, and you can do whatever task the robot needs to do there.
And this is tool identification. To reduce the cognitive load upon the astronaut, we've put this in, especially when on the moon and there are varying degrees of light. We've implemented like a hammer detection. In the future, we plan on implementing more tools. Right. So the future work so far, and this is what we have planned. We plan to complete the remaining designs based on the feedbacks we got from Friday and Monday. We plan to test with other human test subjects at Virginia Tech. And of course, we plan to submit the final report and outreach reports by June 23rd.
Okay, so now for this semester, we did several outreach events aimed at K-12 college students and the Hokie community in Blacksburg. Now, due to our outreach efforts, we won 2 awards recognizing our multidisciplinary aspects in our team. And to show gratitude, we wanted to dedicate a slide to our donors. Any questions?
So it's interesting to me that you guys also picked up on this rover theme. I think it's really acknowledges the fact that I think as we go forward into exploration, it's going to be much more of a human-robotic kind of interaction. And in fact, the next LRV, or what we're calling the LTV, which is our new lunar rover, is going to be a lot more like the Mars rovers than sort of the go-kart that we had back in the Apollo days. So that system's going to be much smarter. And in the 11 months of the year that the crew's not there, it's going to be able to drive around autonomously. So, and even when the crew's there, I think it's going to be nice to have interactions between the crew members and the rover that come in different forms. So it's kind of cool to me to see you guys start to think about what would those interactions look like. So it's interesting.
I love that also. Anytime you can add robotics, it helps because they do more than you can while you're out. I also really like the object detection. I'd be curious to see what, I guess, are you training it right now just to detect certain, obviously, tools, but what are your future plans for that? Also, have you thought about doing it for, with the rover also? So internally, so onboard station, on vessel, or with the rover to detect things. How are you training it, and then what goals are?
Well, we do plan on putting more tools in, especially tools presented to us at the tests, like the rake, the what else? The shovel. Yeah, yeah, we focus on the hammer.
So are you doing it so you hold up the object and it will tell you what it is?
Yes.
Okay.
And that's the plan.
So something that also might be really cool to know or to work on is once you've detected that there is something, if you're looking for it later and can't find it, that would be helpful. Where's the screwdriver in your pocket?
Yeah. We were actually working on detecting the rover, right? I was actually working on making a... it would recognize a cube on top of the rover, and as it's going, the cube would follow the rover, and so you could see it from far away. And then I was implementing a button where you can set a point. If you lose track of a rover, you set the point, and the rover would try to get to that point where you set it. Yeah.
And also when I talk about, for those of you confused why we even did the hammer thing, it was part of our look-on process, the look-ODD process. So at that point, when we got to one of the stations, it was the instructions I gave on Monday was hold the hammer in front of you and then use that for sampling. And like I said, the goal was to do that for the other tools as well.
Yeah, I think that the object recognition has a lot of potential to go some places. I think, just identifying that it's a hammer, you can assume that the astronauts are really well trained and they know what all their tools are. But where is my hammer is really important. The geology field work that I'm doing, half of it is trying to figure out where you put your hammer. We may have some things we currently have our tools tethered to us, but when you're out at a work site, if you think about you've got a bunch of sample bags, you've got a bunch of tools, keeping track of that and making sure we have all of our tools with us. During current EVAs, we do tool bag inventories, and so knowing where that is. Another thing to think about is when you're doing your sample recognition, how you're going to label those samples and then categorize them. So something like, if you can recognize a tool, could you do a QR code that you're holding up, or do some kind of barcode for each one of your samples? That's a really good way to think about tracking your tools and your sample inventory management. I definitely like that. And I had another question for the rover. You said you put spectral recognition on it. Was that a COTS device or?
Yeah, it was.
That's great. I think that's the first time we've maybe seen a scientific sampling instrument on the rover. I think that's going to be really big in the future. So we're definitely going to be looking at spectroscopy, different wavelengths for rock identification. And so linking that back to the astronaut display and recording information is really good. That's great.
Yeah, we had our spectral sensor working last week, and then all of a sudden, when you make changes, it doesn't work. We also had, like Sabrina was talking about, we had a microscope, which we didn't develop a really professional physical mount for, but actually, now that, no offense to all the teams, now coming here and seeing some of these mounts, we should have just brought it anyway and just taped it on. I've prefaced it with saying no offense. But so that was the goal, and the interface that you saw with the picture showing up, it would have been the same thing for all three. It would just showed up in that square, and that was simple. Yeah, so it would just been like 3 types of note taking with the rover.
Yeah, so we used a lot of handheld spectroscopy and handheld microscopes in the field with the European Space Agency. So looking at just what are the COTS instruments out there, we don't have to buy anything super fancy. Maybe having a handheld version of that on your tools cart and then having one on the rover. That's just really great data, and it's not really stuff we had on Apollo. So that's going to be huge for your sample and your site selection.
Yeah, and then just to piggyback on that, our hardware engineer, Raphael, he's not here. He selected that. I don't remember the wavelengths, but he chose a rover that could get the wavelengths for like water, like ice water, and also relevant wavelengths for geology. So he made a good choice in that. Yeah.
Thank you. That was also, my question was regarding the spectroscopy. What I think, so was it a hardware challenge or a software implementation challenge as to why you couldn't execute it? I would like to know for future years, because it's definitely something we're interested in starting to incorporate.
Yeah, so it's actually a matter of plotting the data we're getting, because we were able to get the data from the sensor on the HoloLens, but we're having issues getting the plot to show up, just using the image in Unity.
What do you mean a plot? Like, were you trying to graph the spectroscopy?
Yeah, so for each wavelength, like for the wavelength for red, we had a red line that was plotting it would get 50 data points at a time and then plot those 50 data points on the plot. So the red wavelength would show as a red line, the blue wavelength would show as a blue line. And it was working, and then we made some changes, and we don't know what we did to break it.
Thank you for attempting to implement that. That's also one of those kind of everything we wish to see. So great job on having the forethought to do that and almost getting it to work.
Thank you, everyone, and that concludes our team's presentations.